Yes. So I think we will take this x in terms of length, then it will be slightly easier. Okay. X centimeter, y centimeter. Okay. So this contact resistance, then we are considering there are some wire, additional wire inside of this one. No, I don't think I should take this one. This I will take just x and y ohm, okay, contact resistance. So now actually if you, so L I know, now rho I have to know rho, this I have to find out rho, okay. So this task I have to do, I have to find out rho, okay. So now if say I know rho, either it is supplied or I will measure it. So this part I know, this part also I know, and this also I know. X, y is unknown to me. So I need two equations. I need two equations to solve it and find out the value of x and y, right. So that's why another experiment, just changing the p and q, okay. So 5.2 I will take as a q and 2 I will take as a p. So then another balance point I will find out, So this x plus L1 rho divided by 100 minus L1. So I have to find out balance point for this condition, right. This rho plus y, right. So again these are known except xy, so I will have two equations. From here I will find out x and y, okay. So xy is now I know. Now I have to find out this rho. What is the resistance of this wire per unit length, okay. So length I know, this is the 100 centimeter, okay. So total resistance will be 100 into rho, basically 100 into rho. If this resistance ohm per centimeter, right, then total resistance of this wire will be 100 into rho. So I have to find out rho. So for that we have to perform the second experiment. So in this case what I can do, I can keep this p and q are equal. So 5.2 in both cases, 5.2, okay, p and q, and then I will find out the middle point of this. It should be middle point, but since x and y is there, so it will not be in middle point. I have to find out the length L for this balance point, okay. So after balancing, say I got this length is L or L2, in this case say L2, okay. Then rho, and I have x this side, this will be r, and this other side will be 100 minus L2, into rho plus y, okay. So this is 1, so this equal to this, so x, y, L2 is known to me, right. So then from here I will find out the rho, right. So this way I will find out the resistance per unit length of this meter wire, okay. So now x and y, also rho is known to me for this bridge. So before using this bridge for my measurement, so this is the task I I have to finish. So, how to do that I told you, right. Now, I want to measure the resistance of the platinum wire, right, platinum thermometer. Okay. So, for any metal, the resistance RT, say at a temperature T, RT, so that one can write R0, resistance at temperature 0 is 1 plus alpha T plus beta T square plus gamma T cube, etc., right. So, this is the relation between resistance and the temperature. So, for lower range of temperature, one can take approximately this RT equal to R0 1 plus alpha T, neglecting this other part. But for higher temperature, say in this case platinum resistance generally we use for measuring the higher temperature. Okay. So, if you want to measure say more than 1000 degree centigrade, then I think you should at least we have to consider this beta. So, here our measurement is in the level in the range of say 1 to 300 degree centigrade. So, this is good enough, this approximation is fine for lower range of temperature. So, if this is the relation between the resistance and temperature, so this is the coefficient, platinum thermometer coefficient we tell, temperature coefficient. Okay. So, what I have to know? I have to know what is the resistance at 0 degree centigrade, what is the resistance at 0 degree centigrade. So, I have to know R0, I have to know temperature T, and at that temperature what is the resistance of this platinum wire, right. So, then I have to measure basically RT, T versus RT. Okay. So, that means the thermometer I have to put at different temperature. First I have to put in ice, it is a 0 degree, right. Then I will change the temperature of this thermometer of this platinum wire. So, and different temperatures I have to measure resistance. So, my one task is to measure the resistance. So, to measure the resistance, I will use this bridge, Caddy-Foster bridge. So, what we will do, as I told, these two for platinum wire. So, these two will connect in this third gap 3, okay, third gap, and these two will connect. I think this is PP. So, I think these two PP and these two CC. So, this I will connect at the gap 4, okay, gap 4. Now, in gap 4 additionally I will connect one fractional resistance. This resistance is starting from 0.1, here you can see it started from 0.1 ohm to 10 ohm. Okay. We tell this fractional resistance. Okay. So, to make sure, because remember that if I keep P equal to Q, that I will keep. So, then R equal to S. Okay. So, in R what is there? this platinum resistance plus this two rod connecting rod, that resistance, and here that's only this compensating rod, that resistance is there. So this will be balanced, compensating rod and this connecting rod of platinum wire, that will be compensated, right. But here additional platinum resistance is there, okay. If this with temperature, if this resistance is very high, so you may not get the null point in this within this wire, okay. It may go out, okay. So that's why we use here one fractional resistance, okay. So just some small resistance will put there. So that resistance should be equivalent to the resistance of the platinum at that temperature, okay. So that I will get the null point close to the middle of this, or okay, within 40 to 60, in this range I will get, okay. So this fractional resistance will make sure that this null point, we will find out the null point within this wire, okay. So that's why this compensating wire plus this fractional wire will be connected here, right. Now this bridge is ready to measure the resistance, right, resistance of platinum wire. So now here you can see this thermometer we have put in a water. Now this water is at room temperature. I have thermometer, mercury thermometer. So here I can see this temperature of this water is 20 degrees centigrade, right. So since it is in this water already, so first what we will do, I will measure the resistance of the platinum using this bridge for at this temperature, at room temperature, okay. So first I will do the experiment at room temperature. There is another reason, because I have to do this experiment at ice, right. So if I do the experiment at ice first, then I can go for room temperature. Now problem is to go for room temperature, so it will take time. So to just avoid this wastage of this time, just let me do this, take the reading at room temperature, then I will put ice. I will take, so at room temperature first, then second I will measure the resistance at ice temperature, and third I will measure at boiled water temperature, okay, boiled water, right. So this temperature I have to note down, this 20 degrees centigrade, this is of course 0 degrees centigrade, and this is 100 degrees centigrade, okay. At this 3 temperature I will measure the resistance of the platinum wire, right. So why I need this, at least this 3 measurement? Because what I will do, I will plot graph temperature versus this RT, okay. So at 0 temperature, I will get some reading, okay, and then at 20 say I will get some reading, and at 100, so this is 20 and this say this 100, okay, I will get some reading, okay. So it will be a straight line, right, because this equation is telling this y equal to mx plus c, okay. So in this case I can write RT, I can write RT equal to R0 alpha T plus R0. So, C is R0, so wherever it will cut this axis, so that is basically R0. So, actually we are measuring at 0 degree centigrade, so that's point directly I can take. So, and then this is the mx, this is the m, right, this is the m, slope. So, I will find out slope from this plot, and this slope is basically R0 alpha, R0 alpha. R0 is basically this C here, okay. I know this R0, I know the slope, so I will find out the alpha value. I will find out the alpha value, slope divided by R0, right, slope divided by R0. So, this is the task we have to do, right. So, I think just at one temperature I will, at room temperature I will just show the data, right. So, similar way you can repeat the experiment putting ice, and so we have arrangement to boil the water, right, heater. So, then you have to boil this water and then repeat the measurement, okay. So, I think Mr. Maiti, our lab technical supervisor, he will just show you, he will connect and show you the just one measurement, okay. So, he is connecting, so this in third gap he is connecting this platinum wire, okay. As I told that platinum wire we have to connect in third gap, okay. Okay, then compensating one we have to connect, compensating one we have to connect to the fourth gap, including this fractional resistance, okay. You have to tighten properly. Your tightening means this basically is a shortening of the resistance, you know. This whichever is open, so that is the resistance included there. So, now you see, so I think now you see this galvanometer, this deflection, you can see, okay, see in opposite direction. So, if it is putting in this, if you put, yes, I think if you put at this end, then it is going this side, P by Q equal to R by A, so it is going this other side, right. So, if you put just in middle, close to the middle, so you have to find out the null point. So, no current through the galvanometer, so here you have to take reading, it is 53, okay. So, it is supposed to be this, I think, no, it is at room temperature. So, I think this is fine, this is a 53 is our reading. So, you have to note down this L equal to 53, okay, and you have to note down also this is the 2 ohm, okay. So, fractional resistance is 2 ohm and this L is 53 centimeter. So, you know x, you know y, you know rho of this one. Okay. So, you will be able to find out the R at room temperature, So, what I got? I got this at this temperature, room temperature, I have to note down that is the 20 degrees centigrade. Then balance point I got, balance or null point, I got, null point L equal to 53 centimeter, okay, 53 centimeter. Now, P I have put, P equal to Q equal to 5.2 ohm, okay. X value you have to find out first that you know, so X is this value, Y is this value, so that we have to find out. So, I didn't just didn't show you, but I have explained how to find out, and rho also you know, right. So, you have to write. Now, what you got? P by Q equal to R by S of course. So, in this case your R is this resistance of the platinum thermometer, actually RPT, resistance of platinum thermometer, plus resistance of this rod, where these platinum wires were connected, these two rods. Then you have this X in correction, this contact resistance, and then you have L rho. L is 53. So, I have to note it down, this L equal to 53, whatever we found here. So, this will be the R this side, and other side what is there? Other side is basically you have this fractional resistance. Fractional resistance fractional resistance is, I got I think 2 as I remember, is 2 ohm. Okay. So, 2 ohm resistance, so I can write this as a I can write RF, fractional resistance RF plus resistance of the compensating rod. So, RC I can write RCC compensating rod, okay, RCC I can write, and then I can write plus Y plus 100 minus L into rho, right. So, this is 5.2 by 5.2, so this is 1, right, this is 1. So, that means this equal to this. So, it is assumed that this RCC and R rod, this will be equal, okay. They will compensate, that is the purpose to put this additional 2 rod. So, you can forget this. Now, you see, you know this, you know X, you know L, you know rho, you know this fractional resistance 2, you know Y, you know this L and rho, okay. So, you can find out this RPT, resistance of platinum at this temperature. Similarly, for 0 degree centigrade, you repeat, find out the null point, okay. So, just L will vary. You may need to change this one 2 ohm, may not need. So, one has to find out, instead of 2 ohm, you may need to put 1 ohm or 3 ohm, that you have to see. To get, as I told, to get the null point close to the middle point, just you use this fractional fractional resistance. Okay. So, this way you will get 3 resistance of platinum wire. One is at room temperature, one is at 0 degrees ice temperature, and another is 100 degrees centigrade boil temperature. Okay. So, this is the experiment, very nice experiment, simple experiment, but lot of things one can learn from this experiment. How to use meter bridge, principle of Wheatstone bridge and this meter bridge, and then what is the necessary of additional 2 gap, which then we are telling Carey-Foster bridge, right. And of course, this how to arrange the temperature, how to arrange the change the temperature of the platinum wire. Then here this concept of compensating rod, this is the again unique concept. Okay. So, you can avoid, you can purely measure the platinum resistance. Okay. So, additional connecting wire which also will be affected by the change of temperature and resistance will change. So, it is difficult to deduct this this effect of this resistance. So, that is why the unique way in this experiment is used. So, that is the compensating rod. Using the compensating rod, you can nullify the effect of temperature dependent resistance of the connecting wire or connecting rod. Okay. So, I think yes. So, other part data analysis and then finding out the error of on this measurement, also we have to do that, and I think you know how to do that. So, today I will stop. Thank you for your attention.